Alright, hello students, welcome back to Oceans Robotics. This is section 4 on elastic properties of solids. Please do well to watch section 1, 2 and 3, especially section 1 where we did introduce the topic. We have about 6 questions to answer in this section, section 4, so let's get started. The area under the plot of force against extension E within the proportionality region is equal to the potential energy stored in the stretched elastic string. True or false? Okay, so let's check it out and see. This is how the graph looks like. It starts from the origin. Of course, the region of proportionality region. Now the question is saying that the area under force is here, Newton, and here extension in meters, of course. All right, so the area under the graph is equal to the potential energy stored in the stretched elastic string. So let's see. Now the plane shape we can see here is a triangle, right? And we know that the area of a triangle is half base times height. So half, if the base in this case is f, change in f times the height is what? In this case, the base is the extension. Let's take the height first. The height is this, that's change in f, whereas here is the base, which is E, so times E. Can you recognize this formula or this equation? That's the formula for energy, elastic potential energy stored in a spring. Elastic potential energy, that's half Fe, still remember, is still half Ke squared. Alright, so the area under the plot of F against extension E within the proportionality region is equal to the potential. The answer is true. It's true. So if a piece of wire is stretched until its length doubles, the stress in the wire is equal to the Young's modulus. True or false? So let's see. We know that Young's modulus is equal to stress over strain. That is F. If you follow through up to this point, you would have noticed that FLO, that's the original length, force times the original length, all over the area times the extension. This was the formula we saw in section 1. Now the question now says, if a piece of wire is stretched until its length is doubled. So if the original length is doubled, that means the original length will be equal to the extension. So from here, if we have Young modulus is equal to F, now the original length is this, and the extension is also the same as the original length. Remember, the two of them are equal, so definitely this cancels this, and we are now left with what? Young modulus is equal to F all over A, and this is the stress, so Young modulus will be equal to the stress, so the answer is true. Okay, so a catapult used to hold a stone of mass 500 grams is extended by 20 cm with an applied force F. If the stone leaves with a velocity of 40 meters per second, the value of F is dash. Okay, so here the principle of conservation of energy has to find expression. Alright, the elastic potential energy, alright, has to be converted to kinetic energy. The potential energy stored in the rubber of the catapult, okay, will be converted to kinetic energy once the stone leaves the catapult. So here here we have half Fe. That's the formula for the elastic potential energy in an elastic material is equal to half mv squared. This is the formula for kinetic energy. Okay, so half takes care of half, and we are left with Fe is equal to mv squared. Okay, our concern is to find the force, so F is equal to mv squared all over E. So if we plug in the values, before we do that, let's list out the parameters we have. We have mass is equal to 500 gram. Remember to convert to base unit. So if you divide by 1000, we have 0.5 kilogram. And of course, the extension E is 20 cm, because we have to change to base unit to 100. Sorry, this now becomes meters. Okay, once we convert, and we have what, 0.2 meters. We change the base unit. So let's now go ahead and plug in the values. We have F is equal to, the mass is 0.5, okay, times the velocity is 40 squared, and then the extension is 0.2. So if you work this out, definitely you're gonna get that F is equal to 4,000 Newton, or in standard form you have 4 times 10 raised to power 3 Newton. For a loaded spiral spring, stress increases linearly with strain up until breaking point is attained. True or false? Again, remember, all right, and then the breaking point somewhere is here. Okay, we had this. If you have followed through up to this moment, you'd have noticed that we said that AB is the point, the region of proportionality. Okay, between this and this, Hooke's law is obeyed. All right, that means force is proportional to extension, or you say stress increases linearly or proportional to strain. Remember the second version of Hooke's law. Okay, so it only happens, this is only true up until this point B, not up until the breaking point. So it's false. It's false. The total length of a spring when a mass of 20 gram is hung from its end is 14 cm, while its total length is 16 cm when a mass of 30 gram is hung from the same end. Calculate the unstretched length of the spring, assuming Hooke's law is obeyed. So let's imagine we have this. Okay, now when no mass is attached to the spring, this is the original length of the spring, and then we have like this. Okay, when a mass of 20 gram is attached to it, and then we have like this. Okay, when a mass of 30 gram is attached to it, so the length here is, that's the total length when a mass of 20 gram is hung at the free end is 14 cm, whereas here the length is 16 cm. All right, again we know that extension is equal to, okay, L1 minus L0, which is the original length. Okay, So let's establish our E1 for extension in the first one, this one, in this one. Okay, the extension will be 14 minus the original length, which we don't know, that's what we are looking for. And then E2 on the second one, this one, the extension will be equal to L2 minus L0. So L2 in this case is 16 minus L0. Alright, so remember that force is proportional to E. Of course, force can be the weight force. In this case, it's weight force, which is equal to mg. Now we can say mg, okay, is proportional to E. So mg all over E is equal to mg all over E. Remember, we're establishing the relationship now. So this is 1, m1, E1, G remains the same, m2, m2, E2. Of course, G takes care of G. And then here, the mass, m1 is 20. We have to maintain the unit G since the options carry cm. So 20 all over the extension in this case is 14 minus L0 is equal to m2 is 30 all over 16 minus L0. Okay, so if we cross multiply, we are going to get that 20 times 16 minus L0 is equal to, okay, so let's continue from here. We have a clean slate here. Alright, so again, let me divide this. So from the previous slide, we had that if we cross multiply, we will have 20, okay, times 16 minus L0 is equal to 30. 30 times 14 minus L0. Okay, so if we open the bracket, we are going to get that 20 times 16, okay, minus 20 L0 is equal to 30 times 14 minus 30 L0. Okay, if you tidy this up, you will get 320 minus 420 is equal to minus 30 L0, okay, plus 20 L0. Okay, you have to look very well to see it. This times this is 320, yes, and then this, of course, yes, so we are the right track. So this minus this will give us minus 100 is equal to, and minus 30 L0 plus this will give us minus 10 L0. So L0 will be minus 100 divided by minus 10, and this gives us 10 cm. That should be the answer. A spring of length 25 cm is extended to 30 cm by a load of 150 Newton. It is attached to one of its ends. What is the energy stored in the spring? Again, energy stored in any elastic material is half Fe, is also given by half Ke squared. But in this case, since we are given the length, original length is 25 cm, and original length plus the extension, let's call this one L1, that's 30 cm, and then we have the load or the force, it's 150 Newton. Okay, so it's obvious that we are going to use this particular one. So E is equal to half FE, whereas our extension in this case, extension is equal to L1 minus L0. So that is 30 minus 25, and that gives us what? Gives us 5 cm. We have to change to base unit. So if we divide by 100, 5 divided by 100, that gives us 0.05 meters. So plug that in, you have that E is equal to half times the force or the load, 150, times the extension, which is 0.05. all right, this here, and then this is what? This is 75, then this times this will give us 3.75 joule, and that's the answer. Okay, at Oceans Robotics, we have a team of godly, competent, and reliable teachers to coach and mentor your children with respect to math, physics, and chemistry, and as regards different aspects of coding or programming. So we look forward to hearing from you. Bye-bye.